Welcome to today's Explainer, where we're going to translate the absolute extreme physics of space-time into a visceral first-person descent straight into the dark. Look, black holes are unquestionably the most powerful and extreme objects in our universe. They're wildly weird, deeply complicated, and, honestly, just a little bit terrifying. Today, we're unpacking exactly what they are and embarking on a hypothetical journey right into the belly of the beast.
So, what if you actually fell into one? Okay, let's dive into this crazy hypothetical journey by first establishing how massive dying stars literally break the stage of space and time. You see, space and time aren't just some empty void. We have to think of them as this grand, flexible stage where the universe unfolds. And this stage is not fixed. Matter actually bends space, and that bent space tells matter how to move. When you place heavy things like stars and planets on this stage, it naturally sags underneath them. And that sagging is exactly what we feel as gravity. But what happens when you drop something unimaginably heavy on that exact same stage?
Well, black holes aren't just heavy. They pack so much mass from imploding stars that they act like a literal trapdoor in the fabric of the universe. During the very final moments of a massive star's life, its insides implode at nearly a quarter of the speed of light. This violent process packs so much mass so incredibly close together that it creates a density that essentially snaps the cosmic stage. It forms a strict no-go zone where all our standard, everyday rules of physics just completely fall apart.
Now, to really wrap our heads around this kind of density, consider this staggering number. If you took a black hole with 10 times the mass of our entire sun, all of that immense cosmic weight would be crushed down to a width of barely 60 kilometers. That is 10 of our suns squeezed into an area roughly the size of a large metropolitan city. It's a concentration of mass so incredibly profound that it permanently alters the fabric of reality around it.
And the wildest part is that not even light can escape this border. Because this trapdoor deforms space to such a bizarre extreme, it creates a totally invisible boundary. If you were to look directly at a black hole, it would just look like absolute nothingness. But wait, if it's completely dark, how do we even know it's there? Well, matter orbiting just outside this invisible border can speed up to half the speed of light. The sheer friction from all those particles violently colliding heats them up to 1 billion degrees. This makes the immediate surroundings of a black hole, ironically, incredibly bright.
Section 1. The Descent. As you fall, you're going to experience 3 distinct physics-breaking phenomena before you even cross the point of no return. It isn't just a sudden drop into the dark, it is a gradual, mind-bending distortion of reality itself. Let's break down the 3 wild steps you'll encounter on your descent.
First, as we hover just outside the event horizon, we hit what's called the photon sphere. Right here, gravity is so unimaginably strong that light itself actually orbits the black hole. This creates basically the strangest funhouse mirror in the entire universe. If you looked straight ahead in this region, the light bouncing off your back would travel all the way around the black hole and shoot directly back into your eyes. You would literally be staring at the back of your own head. No way, right?
And this brilliantly illustrates time dilation. Gravity doesn't just warp space, it literally alters the passage of time. As you fall closer, the stronger gravity causes time to pass much slower for you relative to the outside world. From your perspective, you would look up and see the rest of the universe speeding up. You'd be watching eons pass by in moments, taking a freakish one-way time travel trip right into the future. But if your friends were watching you from a safe distance, they would see you moving in ultra-slow motion. Eventually, you just freeze and slowly fade away as your light struggles to escape that immense gravitational pull.
Now, we absolutely have to talk about the physical danger here. If you chose to fall into a smaller black hole, your feet, which are just slightly closer to the center than your head, would feel a significantly stronger pull of gravity. This difference in pull is so extreme it would physically stretch you out. Your body would be squeezed thinner and straighter until you were reduced to a mere stream of hot plasma, completely gobbled up in one final slurp before you ever even reach the event horizon. It's a pretty gruesome process that physicists efficiently call spaghettification. Since this is mostly a huge risk with smaller black holes, for the sake of our journey today, let's just assume you survived the descent by wisely choosing to dive into a massive, supermassive black hole at the center of a galaxy.
Section 2. The Broken Center.
Once you cross that invisible threshold and the entire universe behind you shrinks down to a tiny spot of light, space-time is so horribly broken that time and space effectively swap roles. Every possible forward direction you could possibly move leads only to one place. and that's the absolute center of the black hole. You can't turn around, you cannot thrust your way out. In fact, struggling and firing your rockets only bends your path to bring you to the crushing center even faster. So what's the only way to survive for the absolute longest possible time? Just do nothing. Literally nothing. Just let gravity take you.
At the very center of this nightmare lies this singularity. This is a single point where all the matter that has ever crossed the event horizon is crushed down to something infinitely small. It essentially acts like a fundamental divide-by-zero error in the universe. The curvature of space becomes infinite, density becomes infinite, and all our current scientific rules just completely stop making sense. When matter hits the singularity, it loses all memory of what it once was.
Because past memory is entirely erased, black holes are actually fascinatingly simple from the outside. If you were to somehow collect all the singularities in the universe and put them into a magical physics museum, they would all look fundamentally identical, kind of like electrons. They shed all the complex information of the stars, planets, and unwary space travelers that fell into them, retaining only 3 fundamental properties. Those are their mass, their spin, and their electric charge. That's the whole shebang.
Section 3. The spin cycle.
Now, everything we've discussed so far kind of assumes a stationary black hole, mostly because the math for those is just a lot easier for us to handle. But because black holes are born from violently spinning dying stars, they retain all that angular momentum. As they collapse, they spin up, exactly like an ice skater pulling their arms in. Therefore, real black holes in our universe are spinning at incredible, mind-bending speeds. We're talking sometimes up to 90% the speed of light. This means the reality of a black hole is actually even more screwed up and chaotic than the static models usually get credit for.
This intense rotation completely changes the anatomy of the black hole. The singularity at the center actually swells outward into a ring shape, which is aptly named a ringularity. But even wilder, the rotation is so incredibly powerful that it drags the very fabric of space itself along with it. This creates a terrifying outer region called the ergosphere. If you enter the ergosphere, staying still is literally impossible. It acts like a rushing cosmic whirlpool of space-time with an irresistible tide. You are forced to orbit the black hole whether you want to or not.
Section 4. Fading into nothing. So how does a black hole actually die? To understand their death, we have to look at the very tiniest scales of reality. According to quantum field theory, the seemingly empty vacuum of space is not empty at all. It is constantly boiling with quantum fluctuations. Pairs of particles, matter and antimatter, are constantly popping into existence from absolutely nothing, existing for a fraction of a second, and then colliding and annihilating each other. But when this happens right on the razor's edge of the event horizon, something really incredible happens. One particle can fall into the black hole while the other manages to escape.
This escaping particle is known as Hawking radiation. Now, the universe always demands balance, so the mass of that escaping particle must ultimately come from the black hole itself. Over unimaginable eons, this escaping radiation slowly, meticulously steals mass away from the black hole. And as the black hole shrinks, this process accelerates. The Hawking radiation gets stronger and faster until the tiny remnant of the black hole ultimately evaporates in a massive, blinding flash of high-energy radiation, much like a nuclear bomb. And then, nothing. The trapdoor is just gone.
But hey, don't expect to witness this grand finale anytime soon. Black holes are extremely stubborn. A standard black hole the mass of our sun will last for 10 to the power of 67 years. But the real monsters, the supermassive black holes at the centers of galaxies, have lifetimes spanning a staggering 10 to the power of 100 years. Our human brains are completely ill-equipped to even try and comprehend a number that large.
To even try to picture this massive timescale, let's imagine a cosmic hourglass. Fill this hourglass with one single grain of sand for every single fundamental particle in the entire observable universe. Now that one grain of sand fall to the bottom just once every 10 billion years. If we waited for this entire, impossibly large hourglass to empty completely, not even 1% of a supermassive black hole's life would have passed. That is exactly how long these objects will dominate the dark future of our universe.
So, will we ever truly understand what happens at this singularity? Right now, our math just totally breaks down. But that massive, lingering mystery is exactly why humans do science. And as that cosmic hourglass proves, we have plenty of time left to figure it out before the lights finally go out. What will we discover next? Keep seeking, keep learning, and I'll catch you in the next explainer.